Today we are going to talk about section 6.5, which is on page 685. The first concept we're going to think about is mass and density. This section, for the most part, is talking about stuff in physics that isn't normally covered in calculus or require calculus for the most part. I think, but out of respect for the book, so I'm going to cover it anyway. And then, but I'm just gonna ask you to do the examples, and that should be good enough, okay? And then we'll move on to something that's actually calculus instead of doing some simple physics problems. So let's consider density. Density is, mass and density. Density is defined as of a stick, okay? This of some stick or stick-like object or rod or something is given by this thing is pronounced as rho, I believe. I could be wrong, but who gives a rip? The point is, density is pronounced as given by the function rho times the length of the stick. That will give you what they give you. That gives you the mass, okay? So mass equal to density times length. That density basically means how heavy is it per chunk. And then you add up the whole length, and that gives you the total weight. Mass just means weight. Yeah. Anyway, if the question is, well, normally that's true, but what if the density is not the same the whole time? Okay. Well, what you do is you do the Riemann sum. You take density multiplied by a small chunk of the of your rod, and then you add it all up, which means it's a Riemann sum. So then you integrate the density dx. That from some point A to B, and that is your total mass of your rod that has weird density distribution. So that is the first formula on this following page, where it says m equals the square root. Okay, so that's the mass. Remember, mass means weight. So the weight equals the density times dx, and you integrate it the whole time from the whole range. So having said that, please do example 6.23, which is a one-line answer. Like I said, this stuff is very simple, and it really doesn't need calculus most of the time. But well, your book likes to act like calculus is required, so we'll go ahead and do that. So please do example 6.23. Next, that's the density for a stick. Next, we are going to look at the density of a disk. The disk also has a density distribution. We'll also call it rho. Rho is written like a P, except it looks weird. Okay. So that density, what is that? The density of a disk is such that the rho has a relationship such that the density is the same for each circle around the disk. And you might think, why would that be? We don't know why or care. The point is, that's what it is. So the density is defined by one dimension, even though the disk is in two dimensions. Now, if that were true, then we can calculate the density by calculating each circle and then add it all up. That is, we have a disk, okay? And the density distribution might be different, but it's the same for each circle in it. So what we're going to do is calculate the area of each circle, okay, and then add it all up. And how do you calculate the area of each circle? Each of these thin circles, as the book has drawn a nice picture here. So this circle looks pretty thick, but imagine it to be super thin, okay? Its thickness is only delta x, as it shows here. So we're going to calculate the area of this thin circle, okay, which is, of course, the outside, first let's calculate the area. The area equals to pi times the outside circle, pi xi squared, minus the inside circle, pi xi minus 1 squared. All right, and then by the time you factor this thing out, it ends up being, okay, that's the difference of squares, which becomes a plus and a minus if you are to calculate it out. So then that equals a pi times x, the plus version, okay, xi minus 1, times the minus version. Well, xi minus xiy minus 1 happens to be delta x. Now, how neat is that? So then you already have delta x coming out. And then, so then you use, what is it? Well, we don't even care to mention it. I think this is what? The intermediate value theorem? Maybe? Yeah, I think so. But anyway, we don't even care to quote that. We'll just say that that equals pi times 2 times something in the middle, right? Or the average, whatever, to xi starred. The starred is the average of these two, so two of them equal to the top two added together. So we'll pick one, and remember the xi starred is some point between xi and xi minus 1, and times delta x, and you see where this is going. So the mass then equals to each slice. So the mass equals to the what is the mass? Okay, the mass is the density times that little thin strip, which is, I mean, the thin circle that we're doing the math of. So the mi, just the little bit, okay, the little bit of mass equals to this whole thing times the times your density, okay. That pronounced rho again, rho 2 pi x. Well, I'm just going to say that now we're going to add it all up. xi delta x. I'll write down delta x as dx and xi as x because we're letting n go to the infinity, so the circle thing is getting thinner and thinner. So xi and xi minus 1 are the same thing. And so then we'll just write down it as x, and then the whole thing, then you just, well, integrate, okay? As from, you're integrating from 0 to the radius r. So integrating from 0 to r, and that gives you the total mass of this disk. Yeah, and so now that we have come up with the answer to the how this is done, as you can see, it's done the same way we've always done it. You just have to pay attention to some details in geometry and figure out what the area is, and then multiply by all the stuff you're supposed to multiply, and out comes your formula. And now that we have the formula, the next step is to plug in stuff and find some answers, like example 6.24, which is, as you can see, about 2 or 3 lines, okay, piece of cake. So please do that as your homework. That way, to show your respect for the book. Okay. And then next thing, we're gonna study force. Well, you might not know, like, why does force and why does force times whatever equals to what work, or what does that even mean? It doesn't matter what it means, okay? We're in calculus, not in physics. I'm not saying this because I don't like physics. I love physics, okay? In fact, Openstax has a physics textbook as well that's free, and then after I'm done with the math classes, I'm gonna teach that one too. Even because I took physics in college, so I'm totally able to teach that thing. So, but for now, we're doing calculus, okay? We're not focusing on why force equal to whatever. So then when you study this, you simply just go by what they say. If they said the force times something, distance equal to work, believe it, okay? You'll figure out why later when you study physics. So for now, let's just say that force times what? Force times distance equal to work. Therefore, to calculate, I'm not even going to go over this. It's the same idea, right? If you have a force that's distributed in a weird way, so we try to calculate the force on each delta x and then add it all up like this. See? Force times each delta x, and you add it all up, that will give you the formula of what work is. Don't worry about what that means. That's just the formula, okay? So work equals the force summed up, integrate the force by dx, and from whatever, that gives you something called work. And yeah, that's good enough. And then there is they explain something about Hooke's law, which we are gonna ignore, okay? The point is there's a force and it does something. There's a force, which is, for springs, the force is defined as kx. don't ask why. It's not important. The point is, you apply the force formula and out pops your answer. I mean, look at the integration. It's not necessary to do integration when it comes to force. That's overkill. But yeah, the book wants to do it, so let's do it. As you can see, if you do integration on force, you get a one-line answer. Okay, that's because it's not even necessary. You can just follow the force formula and crank it out. But like I said, if you want to respect the book, please do example 6.25 by yourself. And next, we're going to do pumping water. Now, pumping water is slightly more complicated because it's a volume. So you have to worry about, for example, if you have a tank like this, right? You have the pump volume, and then so you have to calculate the volume, which is slightly more. What's the volume of something like that? Well, it's 2 pi r times thickness of your delta x, and then you sum it all up, and following the formula and stuff, and come up with some formula. Where's my formula? Well, your book didn't even bother giving the formula, but the principle is exactly the same. It's just more tedious, and you gotta calculate your volume is all. And the volume, of course, depends on what kind of tank you got. If you got a weird tank like this, okay, I don't know who has a tank like that. Although I have seen tanks like that, I think. Yeah, sometimes if you drive through the countryside, I believe I've seen a tank that looks like a cone, which, anyway, the point is, if you have a tank, then your volume changes as the depth changes. But other than that, you just take that into consideration, and this whole thing pop out. It's just a matter of detail. The principle is identical. So please do this example, and don't be puzzled if you see a whole page of stuff. I mean, look how much stuff that is. But the whole page of stuff is mostly just calculating the basic geometry, like how wide is that thing at each point, which we have done similar things in the past. So go ahead and read through that, and don't feel intimidated. Just because there's more stuff doesn't mean it's harder. It's just tedious. Okay, grunt work. You're doing a whole pile of grunt work here, and which is what physics has to do a lot of the time, or engineering. So please do that example. What is it called? I don't care. Just do all the examples. Next, hydrostatic force and pressure. The same thing. Okay. The book quotes you the Pascal's principle. You will study more what that means when you study physics. For now, just they give you the formula. Go ahead and believe it. Okay, don't worry about what that means. And then there's the height. You have to calculate dx, the formula, and multiply it together and integrate. And all said and told, you notice after a whole page of talking about it, that look at the actual calculation. Actual calculation is 2 lines. Okay, that's why, because that stuff doesn't require that much integration. It barely requires any integration. So go ahead and do that example 2, and let's see. And that's about it. There is, what is that? The last example about the Hoover Dam. It doesn't, just because it's the Hoover Dam, which is very impressive, doesn't make the math any harder. It does mean you have to pay attention to the basic geometry, though, and like how wide is that thing. So once you got that figured out, okay, and then the problem just is a piece of cake. So let's see. For example, look at part. There are 2 parts to the problem. Part A, 3 lines. Part B, also about 3 lines. So it's just a matter of getting all the details, geometry details worked out. So please do that example, and after that, that should be good enough for this section. Okay, and that's about it.